Okay, I want to recap what we've done so far this module. In the beginning at Module 4-1, we learned how to graph using a table. You'd have your regular function that was set up in any format, and you put in values, some negative, some positive, 1, 0, or your values. You put in something for your independent value, which is x, and outcome would be y, and you graph those ordered pairs. That's a table chart. .com does not like table charts, but to each his own. So you just choose appropriate domains, and you go ahead and figure out what your range is. Then we graph using intercepts, which is one of my favorite ways of doing it. If you have something in standard form, which is ax plus by equals c, this is standard form here, it's sometimes easier to graph using intercepts. Let x equal 0, solve for y. What happens when y equals 0, solve for x. So you graph that. That would be your intercepts. So you'll notice where it hits the axis, where is it hitting the x-axis, where is it hitting the y-axis. Then, we can see here for a second. Then we talked about in 4-2 the rate of change in slope. Rate of change is your way that the graph is slanted. Is it up and right? Is it going positive or is it negative? The rate of change is the ratio between the y value and the x value. So oftentimes we talk about rate of change, and this is going to be a fraction or a ratio. Miles per hour, runs ERA, earned runs. Earned run average is how many earned runs per 7 inning game for softball or 9 inning game for baseball. How many earned runs are scored? So everything is a little bit different. So it's a rate. It's a rate. In this example here, you can compare the rate of change between the year 2000 to 2005, and 2005 to 2010, and so on. So you just talk about rates of change, the ratios, the fraction. That just tells us a lot about what the line is doing in one area. So we talked about the constant rate of change, and we talked about is the rate of change a line or not? Is it a linear function or not? Usually it's linear. Actually, not usually. When you graph basic graphs, it is. When you deal with word problems, it's going to be something like this. It's not linear. So then we talked about slope, biggie, huge thing. Slope, y sub 2 minus y sub 1 divided by x minus x sub 1. That is going to be our rise over our run. The rate of the change in y values divided by the change in x values. And you could do it using the slope intercept formula. And we could count. We'd count down 2 units and to the right so many units, 1, 2, 3, 4, 5 units. And so we'd have, in this case here, the slope is definitely going to be negative because the line is going down from left to right. Sometimes our slopes are going to be 0, as in horizontal. Remember how we spell our horizontal? And sometimes they're going to be vertical. And it fails a vertical line test. It's not a function. The slope is undefined because we cannot have 0 in the denominator. If you notice here, in this case here, a -3 minus a -3 is plus a positive, so I get 0 at the bottom. The denominator, you can't have that in your fraction. Then there's different things we played with the slope. If I gave you a couple points, can you find me what the line is? That is one thing. Pause. Then we learned about slope-intercept form. So you put your positions, you put your equation in y equals mx plus b format. You could find out what your uh, erase it. Thank you. Oh my God, don't even start. You could find out how to graph using the slope and y-intercept, where you decide to start from the b, or the y-intercept, where it hits the y-axis, and then you're able to go ahead and move up or down, left or right, depending upon your slope. So you were given something in standard form, and then we wrote it in slope-intercept form, and we did all things slope. There. Okay, now we're going to go ahead and take our lines and we're going to transform them. We're going to transform some linear functions. So I'm going to switch to this here. Okay, so when we're dealing with linear functions, understand that everything comes from our parent graph. Our parent graph is f of x equals x. So this is our parent graph. Watch this. F of x equals x. That's the parent function, that's the mama function. So when we're dealing with transformations, it's kind of like, oh, that's kind of crazy. Something's going to shift or change, okay? When you're looking at a function, it's important to note how the function is written. If I have a function written, f of x equals the slope times x. F of x equals slope times x. The m is acting as a stretching mechanism. It's a vertical stretching mechanism to the original mama bear function. Okay, here's my original parent function, f of x. If I take a value that is greater than 1 for my slope, that bad boy is going to get tilted. It's going to move up. It's going to approach the y-axis quicker than if it's between 0 and 1. Okay, so understand that when we talk about vertical stretch or compression, we're talking about the relationship that the slope has, okay, where the slope is at. If the slope between 0 and 1, that's a fraction, it's going to look something like this in related to that. If it's greater than 1, it's going to be this way. It's going to approach it faster. And think about it. I mean, if you're talking about the rate at which I could eat chocolate chip cookie dough, this might be the rate. So how many cookies, how many gallons I could eat, not gallons, how many tubs I could eat, not tubs, how many cookies I could eat per hour, might be this. I could eat more than 3 cookies, I'll tell you that right now. But also, if I'm looking at a slower something, like a slower rate, like how much I could eat, how fast I could eat asparagus per hour, it might be something like that. I know, really dumb comparisons, but you understand that's not going to be something as fast. This is a slower rise. This is a way faster rise. Okay. We're talking that's a vertical compression. Okay, it's a vertical compression. So what's happening to that? It's or a stretch, or vertical stretch or vertical compression. Okay, that's what that is called when the graph looks like that. When it's basically just acting. Why is this not working? Acting completely on my parent graph. Okay, so I hit this guy, hit the eraser. Okay, now let's talk about something we get a vertical shift. Very, very shifty. So here's my parent graph right here. Here's f of x. That's the parent graph. You'll notice here, the b is acting as my shifter. The b is acting as the shifter. So if this is where I'm normally at here, my b is my intercept. I'm going to go down a couple of units. I'm going to go up a couple of units, or more than a couple of units, okay? That is my shifter. The graph is still, everything else is exactly the same. I just went up and down that y-axis. Obviously, if the b is positive, I'm going up. If the b is negative, I'm going down. Isn't that interesting? Boys. Okay. Now, hang on one second. So it's important just to be able to look at a graph and know how it's going to look compared to the parent graph. Or if I had an idea as to what the graph should look like, even before I graph it. So for example, if I take a look at this graph, f of x equals 2/3 x. Right off the bat, can you close your eyes and imagine what that's going to look like? Well, here's my parent graph, that's making a 45-degree angle right through my quadrant. Where's it going to go? Will it be above that or below that? Hopefully you have it as showing below that. No idea, will that even work? I'm not showing anything. That's just dumb. And here, if I have 2x, f of x equals 2x, well, my graph will definitely be above the parent graph. If I have our negative 2x, it'll be a slope of -2, so it's going down. Okay? Hang on one second, please. Okay, now I'm going to show you on decimals what these graphs look like, except for the 1/2 x minus 3. Maybe not. Okay, so here I go. Here I have my parent function of f of x. Watch this fun little toy I discovered. I'm so excited. Here I have, oh, you're not there already. Yeah, f of x equals x. That's our parent function, right? And then, oh, I should put that in red. Way smarter. Okay. Well, I thought it was in red. Hang on. Red. There we go. Okay. So our parent function, this is f of x. Okay, good. 2/3 x. 2/3 x. I want to go up a little. Go down a little bit. Okay. There I have my 2/3 x. Now, the exact opposite of that is my negative 2/3 x, and it's going a different direction. The slope is going down from left to right. You'll notice all these other slopes are going up from left to right. This one's going down from left to right. Let's go ahead and take a look at what happens. So when I can take a vertical shift and a compression, excuse me. Hang on, come on. Hang on 1 second. Okay, my computer locked up on that. Didn't like that or anything. So now I'm going to go ahead and shift it. I'm going to take that and I shift it down. If you'll notice here, I went down, my y-intercept's at 0, -3. And I still have my same slope. I could go up 1 and to the right 2, 1, 2. And don't forget these boxes are half unit boxes. So I'm able to go ahead and do that. And I'm still on my same shift, same slope. I could go ahead and do the same thing if I were to have, ooh, I don't know what that is. Let me try type an X like that. If I were to do that, and then instead of having a -3, if I do a +3, but oh, it doesn't like that big X, does it? I think it would. My graph shifted up here. So I'm going up and down the axes. These lines are parallel because the slopes are the same, but yet they're at different intercepts because this is a -3 and that's a +3. So this, I like this summary here. I think this does a really good job. Vertical compressions of the identity happen when the slope is between 0 and 1. Okay. Now, stretches of the identity happen when the slope is greater than 1. So it's a compression when it's between 0 and 1. It's a stretch when it's greater than 1. Now, reflections happen when the slope is negative. So if my slope is one thing, it's positive, the exact opposite. As long as the number is the same, with the exception of the sign, then that's going to be a reflection. Vertical shifts happen when the intercept is not equal to 0. Okay, so I'm shifting when the intercept is not 0, moving up and down, right? Up and down. And transformations can be combined. So I could go ahead and have my slope point up and down, from the compared to the parent graph, as well as move up and down. Let's talk about another type of transformation. And so the last thing I want to share with you really quick is about the horizontal shift. Let me get this tool to work here. The horizontal shift, all the mathematics happens within the function itself. So the b is left alone, but everything happens inside of here, the f of. So it might be x plus f of x plus 2, parentheses, -5. Okay, so when we're dealing with a horizontal shift, it's going to be within the function itself. Here's our vertical shift. Okay, it looks something like that. F of x, x plus 2, f of x minus a half, f of x plus a half, plus 3. That was what we were doing before over here. Okay, so if you'll notice here, in this case over here, we had our slope and our m with our x was right there, but then we added on to that. Okay, that's a little bit different. Hang on one second. So it's important to note that with a horizontal shift, the other one's a vertical shift. This is an example of a vertical shift right here, x plus 3. The horizontal shift, essentially everything occurs within inside the parentheses. So when you see something in the parentheses, that's a horizontal shift. And when you see the horizontal shift, the graph moves opposite of the sign. So if here's my f of x, that's my f of x right here. And if I go to x minus 5, that means I'm going to take my graph, I'm going to move it 5 units. You would think to the left, but it's actually to the right. So horizontal shift is the opposite movement. Let's see, x minus 5 here is actually over here. I'm shifting this direction. If I have the horizontal shift, f of x equals x minus 8, here's my parent graph here. It's going to move 8 units to the right. It's the opposite of that. So if I'm looking at this graph here, it's going to be f of x, I'm going this direction here. That's the horizontal shift. So when you look at your notes, and what I want you to do for your work is I want you to try and read through these. Okay, actually, don't read through those. We'll do these together. But I wanted to share with you just a couple of basic things about the horizontal shifts and about the vertical shifts that are kind of confusing in the text. Okay, I just want you to understand the basic movement. So let's just stop here, and then what we'll do when we meet next is we'll go over these notes together, and we'll skip some stuff, but we'll go over these notes together to get an idea of basic movements of our lines. Again, a transformation is a changing of the line. The line's going to go up, down, left, or right. Okay, it's just kind of changing the shape of where the line is going up, down, left, or right. That's the transformation. Okay, have a good day. Oh, wait, hang on. Hang on. Here's the thing. The phrase that pays. Doc M didn't do anything with the notes as is. Doc M used a different source. So Doc M went crazy. Wait, you can't have that as your line. That'd be a bad one to do. Do this one instead. Well, I'm kind of watching Cobra Kai right now. Cobra Kai is hysterical. Also very dumb and very odd. And if you're an 80s person, you get it. But Cobra Kai, actually, forget Cobra Kai. I want you guys to watch the original Karate Kid. Okay, that's it. Bye.